Today we're going to talk about the forces involved in circular orbits. So let's just look at the moon and the Earth for a second. Let's assume that the moon moves in a perfect circle around the Earth. It's not a perfect circle, but in this case, let's pretend it's a perfect circle. If we look at the moon, let's just look at the moon by itself. What are the forces acting on the moon? Well, we know the moon is going to have some velocity, it's going to be going in this direction. But in terms of the forces, the only force acting on it is the force of gravity, right? And that's going to be the force of gravity from the Earth, right? From the Earth. We also know the Earth is going to have a force of gravity from the moon. But the question we want to ask here is, how fast does the moon need to be traveling around the Earth in order to orbit? Let's assume, for the sake of calculations, simplifying calculations, let's assume that the Earth is just stationary in the middle and the moon is going around it. In reality, that's not exactly how it works, because the Earth pulls on the moon and the moon pulls on the Earth, so the Earth sort of wobbles around a central point. But just to make it simple, let's assume that the Earth stays still and the moon orbits around it. So how can we calculate the speed that the moon orbits? What facts do we need? Well, if we look at this, the path of the moon is a circle. So essentially what we know is that it's going to follow a circular path, and whenever it follows a circular path, we can invoke centripetal motion or uniform circular motion. So we know our centripetal acceleration is v squared over r, but we also know our force, our centripetal force, is mv squared over r, right? Now, if we look at this, this should look sort of familiar. It should sort of look like one of those problems if you have like a string and an object on the end of the string and you start swinging it around in a circle. It's actually a very similar scenario to that. Instead of a string that's holding the two things together, though, it's gravity, right? But it's essentially the same setup, where we have a force towards the center, right, around the circle. So we would call this force here, we would call this the centripetal force. It's really the only force acting on the moon, right? The only external force acting on the moon. So basically what we're saying, in a question like this where an object is orbiting can be defined as moving in a path around an object due to gravity, due to the force of gravity, and nothing else. There's no other external forces, right? It does have a velocity in this direction, but that's not a force, right? The only force is towards the center. So in that case, the force of gravity is the net force, and we know that can also be called the centripetal force. So we know that we can calculate the centripetal force with this calculation, mass times the speed squared over r. And remember, the mass here is the mass of the object that's moving around the circle, right? Because the heavier the object moving around the circle is, the bigger the force needs to be. So I'm going to put a little subscript here with the m. So this is the mass of the moon, right, for that centripetal force. But we also have another way to calculate this force, right? Because it's the force of gravity between these two objects, right? So we also know that we have a gravitational force, which we can calculate as Fg equals g m1 m2 over r squared, right? Now what we just said is that we know this gravitational force is equal to the centripetal force, right? Because it's moving in a circular path. So we can set these equal to each other, the centripetal force and the gravitational force. So on the left, I'm going to put the gravitational force, and it's going to be g m1, so m1 would be the mass of, let's call m1 the mass of the Earth, times the mass of the moon over r squared, and that equals the mass of the moon, v squared, over r. Now, if you want a little bit of a challenge, rearrange that equation, solving for v. You can pause the video here, try to solve for v, unpause it when you think you have an answer. If you simplify correctly, you should end up with this, that this v is equal to g m of the Earth, mass of the Earth, over r, and the square root of that whole thing. So there's a few things to notice about this. This, first of all, we call this the orbital velocity of a satellite. Orbital velocity. And one thing you should notice is, what does it rely on? Well, it relies on g, our universal gravitational constant, which is 6.67 times 10 to the negative 11. it relies on the mass of the Earth, and it relies on the radius, or the distance between the two centers of the objects, center of masses of the objects. But notice how the mass that it's requiring is the mass of the Earth, right? In this case. So in fact, what we're saying is that it doesn't matter what the mass of this object is, the speed that it needs to orbit at that distance is always going to be the same. And that's actually true. You can have the moon here, which has a huge mass, or you can have a 1 kilogram object, the same distance from the Earth, moving at the same speed, and it would follow the same circular path. You could have a space station following the same circular path. It doesn't matter what the size or the mass of the object is, as long as it has the right velocity perpendicular to the planet at the right distance, then you are going to be orbiting in a circle. So that's our equation here, which I put on the page as well. So we call this the orbital speed of a satellite, and that's what the v is. I also put the equation here for t, which, remember, t stands for period, which is the length of time that it takes an object to go around one cycle. So this is the period of the orbit. So it's like how long it takes the thing to orbit. And you'll notice it relies on the same things. So just the radius and the mass. M here again is the mass of the body that's being orbited. So the Earth in this case. And it has a weird 2 pi in it. And 2 pi should sound sort of familiar. The way we actually come up with that equation for the period is we realize that to find the time that the object goes around, if we knew the full distance and we knew the speed, we could find the time, right? Because remember, speed is just distance over time, right? So the time it takes to go around will just be the distance over the speed, right? Now the distance of an orbit, it's just a circle, right? So essentially the distance is the circumference of a circle, right? And the circumference of a circle with radius r is, so delta d would be 2 pi r over v, right? And that's our time of one orbit. And our v is this equation here. So if we plug that in and simplify, you should end up with this equation for the period. You can try that yourself if you want the algebra exercise. So how can we use this? So let's try this example one. So the ISS, the space station, orbits with an altitude of 408 kilometers, and that's the average actual altitude of the space station. The mass of the space station is 4.2 times 10 to the 5 kilograms, and that's the actual mass of the space station. Determine the orbital speed of the ISS. So remember, we have Earth, right? And we have ISS. We'll call it I, right? And the altitude that it's orbiting at is 408 kilometers, right? So we have our equation for orbital speed, which is v equals the square root of gm over r. Okay, so we know what g is, we know what m is, right? It's in the question, right? And we know what r is. Right? We're given the r is the radius is 480 kilometers, right? Well, actually, no, this is a bit of a trick question. All of that information is not what we plug into the equation. I made it a little bit tricky because I wanted you to think a little bit. Is 408 the radius that we're looking for in this question for the r? Well, remember, when we find the force of gravity between two objects, we're always looking for the force of gravity the distance between the centers of the two objects, right? What the 408 kilometers is the altitude of the space station, right? That means how far it is from the surface of Earth, not from the center of Earth. So I'm actually going to erase this diagram here. It's not a very good diagram. I'm going to draw it a little bit more to scale, where we have the Earth here is this big thing, and then we have the space station floating up here at 408 kilometers, right? Well, how do we find the radius or the distance to the center of mass? Well, we're going to need to know the radius of the Earth, right? Because the center of the Earth is somewhere way over here. So the distance it is from the center of mass is actually the radius of the Earth plus this altitude, right? So just looking it up, the radius of the Earth is 6,371 kilometers. And I would give that to you in a question on a test or whatever, obviously. I just wanted to trick you a little bit for this question, because I gave you a distance, but it wasn't the right distance. So to find the radius, the r that we need to plug into the equation, it's just going to be the radius of the Earth, 6,371, plus the 408 kilometers. And then we should also, so this is kilometers, we should convert it to meters. And if you do that, you're going to get 6.779 times 10 to the 6 meters. So that's our r that we plug in. We know what g is, that's 6.67 times 10 to the negative 11. What about m? Which m do we plug in? Do we plug in the mass of the space station? Well, no, we don't. Remember, when we did this question, the mass of the object that's orbiting, the satellite, it actually cancels out. It doesn't end up in our final equation. It doesn't matter what it is. So what mass do we need here? We actually need the mass of the Earth, which, again, it's another thing we can look up. I'll put ME for mass of Earth. The mass is 5.97 times 10 to the 24. Okay? So I gave you this as a bit of a misdirect. That actually won't influence the actual the orbital speed or the period of the space station at all. So we can do the calculation now, right? 6.67 times 10 to the negative 11 times mass, which is in kilograms, so we're okay. So times 5.97 times 10 to the 24, all over the radius, which is 6.779 times 10 to the 6, which is in meters, so we're good. And we can do that calculation. When you do that, you get that the orbital speed is 7,600, round it to two significant digits, about 7,700 kilometers, meters per second, right? Because we're working with meters and seconds. So that's the orbital speed of the space station, and that's actually very close to the orbital speed of the space station if we were to just look it up. So keep in mind, that's 7 kilometers per second. It's almost 8 kilometers every second that the space station is traveling. So that is very, very, very fast. And in fact, that's the hard part about putting the space station up into orbit, is that in order for it to orbit, it needs to be moving at that speed. If it's moving slower, it's not going to orbit. It's going to fall back down to Earth. So to be at an altitude of 408 kilometers, you need to be moving at that speed. Essentially, that's what that means. So the question actually also asks us for the period, which is t. This is easy because we already have everything that we need to calculate it. It's just r cubed over gm, right? So again, if we plug everything in, you should try it yourself as well. We should get a final answer of 5,600 seconds, right? Now, what is that in a more convenient unit? Because we don't know. What's 5,600 seconds? I don't know. I happen to know, though, that there's 3,600 seconds per hour, right? Because it's 60 times 60, so 60 minutes times 60 seconds, which gives you 3,600 seconds per hour. So if we divide by 3,600, that's going to give us approximately 1.5 hours. So it takes approximately 1.5 hours for the space station to go around the Earth once. And this might be a stat that you've heard before. Basically, they can go around the Earth in like 16 times in one day, essentially, because of how fast they're going. So there we go. Now, the next question says, what would happen to the orbit if the ISS were to slow down or speed up, sort of, all at once? So I'm going to do this one off to the side. We have a little more space here. If I have the Earth right here, and I have the space station, we'll call it I again, and it's traveling in this circular path, right? Let's pretend that's a perfect circle with radius r. If you were to slow down, the space station's at this point, let's say in the orbit, and it was to slow down by 50 meters per second or something like that, what would happen? Well, what would actually happen as you slow down the space station is that the orbit would lower. It's going to go into a lower orbit. It's going to fall. It's as if you're standing up here. It's as if you're standing up here on a very high tower that's 400 kilometers up, and you threw the ball with less speed than it would take to go around the Earth. Well, what would happen is you'd still orbit from the same point, but your orbit would actually go lower on the other side of Earth, and then it would make it back up to the same point. So you actually would lower your orbit. And if you lowered it too much, if you slowed it down too much, you're going to intercept the atmosphere of Earth. If the atmosphere is like around Earth like this, the atmosphere only goes up about 100 kilometers. But if you intercept that atmosphere, obviously that's very bad for the space station. It's not meant to re-enter Earth's atmosphere, so it'll probably break up on entry. So you don't want to do that. And if you slow down so much, you're going to end up just sort of intersecting right with Earth, which would be obviously a very bad thing as well. If, on the other hand, you sped up the orbit, what do you think is going to happen? If you increase the speed of the space station? Well, what you do then is it's like you're throwing the ball at a faster speed. You'd actually make the orbit more elliptical. It wouldn't be circular anymore. So this is called raising the orbit of the space station. And they actually do this because even though the space station is 400 kilometers up and space only goes about to 100 kilometers up, there still is a little bit of atmosphere up there with the space station. It's very, very, very thin. There's just, very little particles, but it slows it down enough that every once in a while they need to use the thrusters to boost it back up to this sort of white orbit I have here. So they need to do that every once in a while. So that's sort of how orbits work. Again, in this course, we're only going to be focused on circular orbits. If you take more advanced stuff in university, like aerospace and stuff like that, you will talk more about elliptical orbits. Okay, let's go on to the next question. How fast would you have to throw a baseball horizontally to make it orbit on the surface of Earth? So, if you think about it, if you're standing on the surface of Earth, right, if this is Earth right here, let's do Earth in this blue color again. If you're standing on the surface of Earth, so let's put us in right here, and you threw a baseball horizontally, right? Well, it would fall back down. This is obviously very exaggerated, right? But it would fall back down. If you were to throw it faster, it would probably go a little bit further. If you threw it even faster, it would go a little bit further. But there's a certain point, if you threw it so fast, it would basically miss the Earth. It would keep going and go all the way around. That was a horrible circle, but it's supposed to be a circle because that's what an orbit is. It's like you're throwing an object horizontally so fast that it never reaches the Earth again. It just orbits. And you can calculate that's the same thing we just calculated above. We calculated at an altitude of, about 400 kilometers. So can we find out how fast it would have to be on the surface of Earth? Well, we can use the exact same calculation. So the calculation was, it's that same one up there. So it was V equals the square root of GM over R. And in this case, the radius we're looking at, basically we're saying we're standing on the surface of Earth, right? So the radius we're looking at is basically just the radius of Earth. No altitude needed. And the radius of Earth, it's right up here, 6,371 kilometers. So plugging everything into our equation, right? Square root of 6.67 times 10 to the negative 11 times the mass of Earth, once again, 5.97 times 10 to the 24, all over the radius of Earth, which is 6.371 times 10 to the 6, right? If we convert that to meters. So if we do that calculation, first of all, before we do the calculation, do you think it's going to be faster than the space station, which was 7,700 meters per second, or it's going to be slower than the space station? We're at a lower altitude, make a prediction, and then calculate it. And then I'll show the answer. So when I do that, I get about, rounded to two significant digits, 7,900 meters per second. There we go. So you need to throw a baseball at 7,900 meters per second, 7.9, pretty much 8 kilometers per second horizontally at the surface of Earth to make it orbit. Now, is that possible? No, it's not possible. If you try throwing a baseball that fast, that's multiple times the speed of sound. Basically, I think you'd incinerate the ball because it would be going so fast through the atmosphere. That fast, if you're going that fast through air, air sort of is like a brick wall. It doesn't want to move out of the way. It can't move out of the way that fast. So basically you're going to incinerate the baseball way before it makes its way around the Earth. But theoretically, if there was no atmosphere, you could, right? So it seems like this is a higher number than it was for the space station, right? So what it seems to be is the higher up you go away from Earth, the higher up you go, the slower you need to go to orbit. So a satellite up here will need to go, this is the space station, 7,700 meters per second. If you keep going further away and you want to orbit in a circular orbit, it's going to be less and less. Up here it might be like 3,000 meters per second. And if you keep going more and more, further and further away, to get a circular orbit, it's going to be slower and slower. It might be like 100 meters per second all the way out here. Until eventually you get to a point where you're at like 1 meter per second in order to orbit. And that orbit would take a very, very long time to get around the Earth. But if you're at the point, there's actually a point where it's going to be 0 meters per second, like basically 0, because if you go any faster or any further, you're going to end up escaping Earth's gravity altogether. So this is sort of like the limit of how far away you can orbit the Earth with a circular orbit. Sort of interesting. Getting back to the question now. How does this differ on the surface of the moon? What do you think? What's going to be different about this equation on the surface of the moon? What do you think? Well, I'm just Googling right now the thing that we need to plug in for that. What's the only thing in the equation that changes? Well, there's two things in the equation that change, actually, because the moon has a different mass than the Earth, and it also has a different radius than the Earth, right? So we need to know both the radius and the mass of the moon. So the radius of the moon is 1,737 kilometers. So 1.737 times 10 to the 6 meters. Oops. Now it's a little bit hard to see, but it's 1.737 times 10 to the 6 meters. So it's about a quarter of the radius of Earth, actually. And then the mass of the moon is 7.35 times 10 to the 22 kilograms. Now, I want you to make a prediction. Is it going to be slower or faster than this? Because something you got to think about is that as the radius gets smaller, right, we have to throw it faster and faster and faster, as we just talked about, because the radius is in the denominator. It's being divided. So the smaller the radius is, the faster the velocity is going to have to be. But the mass of the moon is much smaller than the mass of the Earth, right? And mass is in the numerator. So that means as the mass of the planet decreases, the speed that you need also decreases. So this is like a factor that's going to increase the speed. This is a factor that's going to decrease the speed. So what do you think? Is it going to be less or more or about the same in order to orbit something on the surface of the moon? Well, let's calculate it. Same calculation, square root of gm over r, where m is the mass of the object that's being orbited. And we can do the calculation. I'm actually going to let you do the calculation here. I'll pause the video. You can pause the video. Unpause it when you have an answer, and you can check with mine. So I got about, to two significant digits, 1,700 meters per second. So it's actually much, much, much slower. And the reason for that is because the mass, even though the radius is about a quarter of the radius of Earth, the mass is actually much less than a quarter of the mass of Earth. So that's why. And you should also notice this. If you've ever seen the videos of the Apollo missions when they landed on the moon, first of all, the astronauts can hop a lot easier on the moon, right? The gravitational field strength is a lot less on the moon. So it's a lot easier to bounce higher, or in other words, throw a ball. They actually brought a golf club and a golf ball to the moon, and they shot some golf balls, and it's much easier to get a golf ball to go further on the moon than on Earth. Now, on the moon, 1,700 meters per second, the moon doesn't have an atmosphere. So you could theoretically orbit something on the moon if you threw it fast enough. Now, no human being could hit any object at 1700 meters per second. It's very, very, very fast. But if you had some sort of cannon that you brought to the moon, you absolutely could orbit something just by launching it from ground level, and it would come back all the way around and hit you in the back of the head. There you go. Cool. That is your introduction to circular orbits. Remember, these calculations only work for circular orbits. If there are any other orbits, the calculations get a little bit more complicated.